Okay, so the key to understanding logarithms, or logs for short, is basically understanding that it's just a different representation. So do you agree, you don't have to write this, but do you agree that 1/2 is equivalent to 0.5? All right, so these don't look anything alike. We have a fraction and we have a decimal, but they are the same value. They are equivalent to one another. So what logarithms are equivalent to something that you do have a lot of experience with. So we'll talk about what the algebraic implications of that look like. For right now, I'm going to show you this picture, and you can sketch this as we talk about it. The red function is the exponential function. We learned about this last week. It's got an asymptote at y equals 0. It's got that exponential growth shooting up very quickly. And it has the equation y equals 2 to the x power. So I want to be clear that y equals x squared is not considered an exponential function. Just because it has an exponent doesn't mean it is exponential. What kind of function is y equals x squared?
Parabola.
It makes a parabola. What do you call it? There you go. Okay. So y equals x squared is a quadratic. Exponential equations end up having your exponent is the input. And of course your base, like we talked about, the base of e, or a base of, in this case, 2 or 3 or 4, right? Like that, the main idea is that your exponent is the variable. So our exponential function in this picture is the red one, y equals 2 to the x power. Algebraically, what do you notice about this exponential red function and the blue function? Algebraically, y equals 2 to the x power, and then x equals 2 to the y power. Yes, very good, Zach. Those are inverse functions. Inverse functions. And that's exactly what a logarithmic function is. It's the inverse to an exponential function. And its graph, since we exchange x for y, its graph is a reflection across the line y equals x. Okay, now algebraically, whenever we find the inverse of something, we resolve for y. So like you have y equals 2 to the x power. When you resolve for y and you get x equals 2 to the y power, typically when you have exponents, you like undo the exponent by taking a root. But taking, like, I'll say the y-th root, that doesn't even sound normal, doesn't even make sense, isn't really the thing to do. And that's kind of what allows us to define a logarithm. So if the logarithmic function is the inverse, basically you have this definition. An exponential equation is written in the form y equals b to the x power. And this is stripped down to its core, right? Like last week we talked about a times b to the x minus h power plus k. But this is just stripped down to the very, very basics. No a, no h and k movement. If this is an exponential function, then we can define the logarithmic equation as log base b of y equals x. And when you write it, b is the base. Okay, so b is a subscript. And then y and x are just like regular size, right in line with the word log. Now, this is true for b's that are greater than 1. Okay, if b's are positive, or sorry, if b's were negative, then it's a really, really gray area, because if you have the number, or if you have -2 as a base, if you raise -2 inclusive, right, so in parentheses -2 squared, you end up with a positive number. But if you do -2 cubed, then your answer ends up being negative. So negative bases are a really, really gray area for logs. So they are only defined for b's that are greater than 1. the way that you say this, if you don't know how to say that, or if you didn't remember, or you wouldn't know how to say it if you saw it, I would write down like actually what to say when you approach this equation. Log base b of y equals x. Does this ring a bell from last year?
Yeah.
Okay. At least for Zach it does. For the rest of you, maybe. And Tyler. Okay, I didn't hear Tyler. Okay, and again, it's the most uncomfortable part about it is that it kind of has a word in it, right? Like we use the abbreviation log, but you just have to get comfortable with how the variables, ooh, that sounds lovely, how the variables locations are changed in order to write it into the other form. So again, it's as simple as fractions and decimals being the same amounts, but just have a different look to it. So we're going to do a couple of examples of switching back and forth between the forms. So I'm going to give you a couple logarithmic equations, and I want you to switch it to exponential. Log base 7 of 49 is equal to 2. And then the log base 8 of 2 is equal to 1/3. So I want you to switch these exponential equations and put them into logarithmic form. Some of you are going to catch on to this pretty easy. Some of you are going to always just kind of hesitate and look back to, I'll say, like the equation to make sure you're doing it right. The key is starting with the base. Okay, so like base 7 is the same as the base for your exponent. So if you have 7, and then just use your logic, guys. It's going to be 7 to the something power equals something. Well, 7 to the 49th power is not equal to 2, but 7 squared is equal to 49. And all I'm doing is taking these variables, right? If this is b, this is y, and this is x, and I'm rearranging them into the exponential equation. 7 squared equals 49. Log base 8 of 2 equals 1/3. Same thing. Start with your base. So I've got 8, and then 8 to the 1/3 power is equal to 2. So that's going from logarithmic to exponential. Now let's go the other way. From exponential to logarithmic, I want you to convert 2 to the 5th power equals 32. And then 3 to the negative 3rd power equals 1/27. I think this direction is a little bit more challenging because it's less intuitive when you have to figure out how to piece the 3 numbers together in the log. Going to exponential, you just try to make a logical statement using those 3 numbers. In the other direction, again, it's just important to start with the base. So in this case, for part, why did I label this B? For part A, your base is 2. So I know I'm going to have log base 2. And then you have to just figure out where the other 2 numbers go. The exponent always goes on the inside. I'm sorry, not the exponent. Whatever it's equal to goes on the inside. And then the exponent is what's isolated. So it's equal to 5. Part B, 3 to the negative 3rd power is 137. Again, start with your base. This is going to be log base 3 of 1/27 is equal to negative 3. Any questions on converting? All right. Next, we're going to evaluate, which sounds exactly like, which is exactly like it sounds like. I want you to just tell me what number this is equivalent to. So I want you to evaluate log base 5 of 1/25. This is also a good time for me to remind you that your calculator does have logarithmic properties that you can calculate logs. Very straightforward, very easy. But these would be the types of questions that I would give you on the non-calculator portion of your test. So you've got to make sure how to use just the properties of transforming them to solve and simplify. So what I would do is anytime I ask you to evaluate, I'm basically asking you what value is equivalent to this. In other words, that's like basically me saying log base 5 of 1/25 is equal to what value x. So anytime you evaluate, essentially what you want to do is set equal to x and solve. So get x by itself. Not only do you want to solve, but in order to solve, that will probably involve just convert to exponential form. Because we kind of understand exponents a lot better than we can understand logs. So if I convert this to exponential form, my base is 5. So that would be 5 to the x power is equal to 1/25. Now, some of you may know the answer right away, and that's okay if you do. I at least need to see this step. If you aren't sure of the answer right away, your job is to figure out how you can rewrite 1/25 to also have a base of x, or sorry, a base of 5. So how can you rewrite 1/25 using a base of 5? Yeah, 5 to the negative second. You may take an intermittent step and say, okay, I know 1/25 is 1/5 squared, and then 1/5 squared is the same thing as 5 to the negative second power. And then when you get down to this part, you're golden. Your bases are the same, which implies that your exponents must also be the same. So if I have 5 to something power and 5 to something else power, because my bases are the same, the exponents must be equivalent. So in order for these two things to be equal, x, the variable, must be -2. All right, so now let's talk about properties of logs. Again, I want to remind you that logs are a different representation of exponents. So these properties are going to look very, very familiar to you, and pretty much they're going to be manipulating the exponential properties that we already know. First one is going to be the product property. The product property is this: log base b of m times n is equal to. Now, remind me, when you're multiplying numbers that have the same base, what do you do with their exponents? You add them. Well, this is the same thing, except our exponents just look weird. They're written in kind of a different format, but you do the same thing. You would take log base b of m and add it to log base b of n. Similarly, we have the quotient property, which is when you're dividing numbers, so log base b of m divided by n. And the property when you are dividing numbers, you subtract their exponents. So this would be log base b of m minus log base b of n. And then we've got the power property. So when you have a power to a power, you have a number with a base and exponent to a power, what do you do with the exponents?
Multiply.
Okay, so if we multiply and I give you log base b of m to the p power, you would bring p out front to have p times log base b of m. And then our last property is arguably the most important. You're pretty much going to use it on every type of solution problem that we're going to have, and it's the property of equality. It says, if log base b of m is equal to log base b of n, then m must equal n. And that's essentially what we did in the example that we just finished, right? We got 5 to the x power equals 5 to the negative second power. So in those cases, we ended up having the same base of 5, which meant that the exponents would have to be equivalent as well to make that equation true. So here are your properties. And we're going to do 4 examples practicing how to use them. All right, here we go. Example A. I want you to solve log base 10 of the cubed root of 10 is equal to x. Okay, if you look at your properties that you have here, none of them are really going to be helpful because all these properties involve like the log of a number times a number or a number divided by a number. I guess technically you could rewrite this as m to the p power, so you could rewrite it as 10 to the, instead of the cubed root, what is that the same thing as? As an exponent. What is the cubed root?
1/3.
Okay, so you could rewrite that as log base 10 of 10 to the 1/3 power, and then you get 1/3 times log base 10 of 10. But then you'd have to know some properties about base 10 and common logs, which we're not going to talk about until tomorrow. So at this point, I would say let's forego the properties and just use the strategies that we did earlier, which is let's go ahead and convert this to exponential form. If you convert this to exponential form, you take your base, which is 10, to the exponent, which is x, and set that equal to the cubed root of 10. Now, just like we did earlier, if we get our bases to be equivalent, then the exponents are going to be equivalent. So if I do 10 to the x power, you guys just reminded me that taking the cubed root of something is the same as raising it to the 1/3 power. So if you can rewrite this as 10 to the x equals 10 to the 1/3, then again, I have the same basis, 10 and 10, which implies that my exponents must also be the same. Then x must equal 1/3. Okay, example B. Log base 6 of 4x plus 6 is equal to log base 6 of 8x minus 2. Which property do you think is going to be most benefit to us?
Quality.
Equality. You've got a log of something equals a log of something else. And the good news is those bases are the same. So I've got log base 6 and log base 6. And that equality statement says if you have log of the same base, then the stuff on the inside must also be equivalent. So then 4x plus 6 must equal 8x minus 2. And then this just becomes like a very basic algebra problem. We just got to solve. So subtract 4x from both sides. Add 2 to both sides. You end up with 8 is equal to 4x. Divide both sides by 4, and you get that x is equal to 2. So that's as pretty much easy as it gets in terms of not having to really manipulate anything. Any questions so far? Okay. Next example. Log base 9 of x plus log base 9 of x minus 2 is equal to log base 9 of 3. Now this one has another term compared to the last example. All of them are base 9, which is good because that means we can apply our properties. The operation that we need to pay attention to is the fact that 2 of these logs are being added. When that happens, the property says we can rewrite or combine those two terms, if you will, into one as the log base 9 of x times x minus 2. So the property says let's just multiply its two components together, and that is equal to log base 9 of 3. Now you do have it to where you have log of something equals log of something else. They have the same bases, so then you can set the contents on the inside equal to each other. The only thing you got to be careful of is making sure that you distribute this x. Okay, so when you, and you can even skip this step altogether if you want, as long as you make sure that x is distributed. So when we distribute it, we get x squared minus 2x equals 3. And then your job is just to solve for x. Anytime we see a squared term, pretty much, if you can't factor out something using GCF, probably implies that we're going to use the sum and product rule. So we want to have everything set equal to 0 in order to factor and solve. So the sum and product, two numbers that multiply to be -3, add to be -2. Okay, so -3 and +1. And then that implies that our values are going to be x is equal to 3 and x is equal to -1. Now, earlier we discussed about the whole idea that you cannot have a base that is less or 0 or less than 1. The other thing is this: you cannot have the log of a negative value. And again, reason is just that discrepancy of negative numbers being raised to other exponents. So anytime you end up with a variable that would cause us to have the log of a negative number. So if I plug in -1, this would be log of -1. This would be log of -3. Log of negative value does not exist. So if the log of your negative value does not exist, then you're going to throw out x is equal to -1, leaving us just with the answer x is equal to 3. Okay, last example. Log base 8 of 48 minus log base 8 of w equals log base 8 of 6. Operation to pay attention to here is subtraction. If you have two logs that are being subtracted to each other, the property of the quotient property says that when you subtract these two logs, then we can combine two of them to be rewritten as log base 8 of 48 divided by w, which is equal to log base 8 of 6. And then once you've accomplished this, then we know that our inside terms are equal to each other. So if you have 48 divided by w is equal to 6, you can just logic your way through this, right? 48 divided by what term gives you 6, or put 6 over 1 and cross multiply, however you want to think about it. Either way, you get w is equal to 8. So a couple notes and things to think about. Again, many of you are going to get pretty quick at these, and I do want to encourage you to at least show something. Okay, so pretty much every single question has some sort of intermittent step that you're probably doing mentally that I need to at least see that's helping you get that final answer. So if I do my problem in 5, but you can only do it in 1 or 2, that's fine. I've also had good questions earlier today asking if I will ever give you a question that involves bases that are not the same. And the answer is maybe. Now, I won't give you a solution because I haven't told you how to change those bases quite yet, but I might give you something like a question to simplify. And I might say, okay, log base 7 of x minus log base 2 of 5 plus log base 7 of 3. And if I ask you to simplify that, you can use some of your properties, but only for the bases that are the same. So if I have log base 7 of x plus log base 7 of 3, those two can be rewritten as log base 7 of 3x, right? 3 times x using that property. But the minus log base 2 of 5 cannot be combined because that technically, that's just like exponents that don't have the same base. So that would be like as far as we can go. So if I'm going to give you something with a different base, it would just be like a simplifying question, and you would have to know that you can only use those properties to combine terms that have the same bases.